So today we'll be diving deep, we'll be going further, and we'll be talking. So we'll be looking at connections, standalone connections. How do these devices communicate when it comes to access control, when it comes to security solutions? How do device communicate? How do this system work? So those are the things we'll be looking at, and I want us to really pay attention because it's really important to really understand these parts. So I term this. Let me turn on my video so everyone can see me. Yeah, can you all hear me now? Yeah, okay. So if my voice is breaking, please first do well to check your network so I won't have to pause, So yeah, so I named this from pink to power because if you look at the digital, some people are still saying I'm breaking. Hello. If you can hear me, please send a reaction. If you can hear me clearly without me breaking, please send a reaction. Okay. So one of the reasons why I named the theme of today's section, Pink to Power, is because it's important to understand why we have security controls and how security controls have been, have transcended from the ages of to use the padlock systems and all that, from those ages to now putting in computerized systems to actually aid. Okay, can anyone hear me now? I just changed my network, so I think I should be clear now, very clear now.
Yeah, very clear now.
Okay, yeah, very good. So we started from the ages of, so I'm going to share it out now. Okay. So when security systems started, it all started from the ages of, having a padlocks kind of system, a manual padlock. And one of the issues with this is that the security that borders around having a system like this is not quite efficient, right? Quite efficient in the sense that, say, for example, you are using a system like this in an area where you have hoodlums, and you are storing, say, 300 million naira, right, in a safe in that area, and people saw you as you are coming in with that amount, then you now get a padlock system like this, and then you now use it to lock that area. And let's say you now hire a security guard, right, to watch over that area. One of the things that would happen is, first, you can't fully trust the security guard. The security guard can hand over the key to someone else and say, "Oh, you know what? Hold this key. Let me go and do uh, something. Let me go and find some activities to do." And the security guard can, also be part of those people that would uh, that would be involved in, taking away your money, and uh, the introduction of this back then was to aid in a system where you can have your properties guarded in an automated way. And the automated way as it is back then was to make use of systems like this. But the shortcomings of systems like this is that you need human interference. Human interference in the sense that even if you put a padlock, you still need someone to always help you guard that place, right? So how do we move away from this system? How do we move to a system that is much more automated, right? That doesn't need human interaction, right? That is that gives you that gives a layer of added trust to the system, right? That works completely on a zero trust principle. Then that is where we have that is where we introduce the what we call the access control, integrated access control systems. So with an integrated access control systems, we are looking at a system where there's a digitalized infusion of every control logic I want. And with those systems digitalized, that digitalization can now work with whatever manual implementation I'm putting into place. So it doesn't really eliminate this. It just serves as an added trust layer to aid with this. And how do we achieve that? So if we look at the slide, the journey of this form of verification, right, is because if you look at this guy here, this padlock here, and I come to my slide here, you see that at the end of it, the mechanism that guards against security controls are still in form of mechanical locks. All the layers we've added to ensure that our solution stays digitized is to make those layers as computerized as possible in order to ensure that the mechanical movements of this particular layer are automated. So if you look at the journey of verification, the first principle is you have a terminal, right? And users present fingerprints or card on the terminal. From our last class, this terminal looks like what? Can anybody tell me what this terminal looks like? A model this terminal looks like? Can anyone tell me what model of device
F18.
does this terminal looks like?
F18.
Yeah,
F18.
You have 15 device.
F F18 device.
F18.
Good.
Yeah.
Yeah, very good.
F18.
Very good. Good, good, very good, very good. Thumbs up, everybody. Let me thumbs up for everybody. Let me thumbs up for everybody. Yeah. So it shows we are really following.
Even
Yeah.
So we have a system where user present fingerprint or card, right? So what happens when you badge your card on the device or when you press your fingerprint on the device? What happens is that when you badge, the device cross-reference your card or your fingerprint. It cross-references against an ID that has already been stored. So for devices like this, say I want to register myself. I take this device, I get my card, I register my card on that device, I register my fingerprint on the device. What happens next is, if I'm coming next time to access on that device, the device already has my fingerprint details. It already has my card details. So what it does is that when I badge my card on the device, or when I put my fingerprints for access on the device, what happens is that the device will cross-reference my card ID, and my fingerprint. So my card ID is basically just sequence of numbers, like something like this. So you have your card, like this color. So you have your card, and your card, say, your card will come in a sequence of number like 15 something something. So these numbers, they are stored on the device, right? They are stored on the device. Let's say this is the device. So this number that's stored on the device. So when a user comes to badge their fingerprints on the device, a user with that same ID comes to badge their fingerprint on the device, what happens is that the device would cross-check that fingerprint or that card. So for card, it's easier because card is sending that bit of information to the device. For fingerprints is getting translated into image. The image is converted into base 64. The base 64 converts into your numbers. So those numbers are translated by the device. So those numbers are now translated into bits. Those bits are what you see 0, 1, 0, 1. So if there is access, if the instruction is when you badge a card on the device, send a short pulse of electrical circuit to the relay to trigger this door to unlock. Then what the device will do is that after verifying your details against the ID that has been stored in it, and it sees that it matches, right? The device will now send a short pulse of electrical signal, sends it to the relay, then the relay will now trigger the door to unlock or not unlock. So that's the simple process that happens. You have user present fingerprint or card, device cross-references ID against digital firmware rules. Then the specific actions are executed. You want to verify access, you want to grant or deny access. So when access is granted, the relay gets triggered. So we are going to go into how the relay also works. I'm going to explain that to you guys. So access control is the instantaneous translation of digital authority into mechanical action. So all these things I've described here, the simple definition is what is here, which is access control is the instantaneous translation of digital authority into mechanical actions, right? So just like I explained here, this is the mechanical part, right? And what we are introducing is an integrated digital layer, right? So we are introducing this digital layer. We have our what? We have our padlock here, our mechanical padlock, and we are introducing this digital layer. So that definition should stick with you always. This simple definition, access control is the instantaneous translation of digital authority into mechanical action. Digital authority examples are, I want this person to have access. I don't want this person to have access. What should happen, right? So 1 minute, please. All right. So access control is the instantaneous translation of digital authority into mechanical actions. I want you to take that as a commandment. All right. So one thing we also want to look at is that there are different types in which access control are wired, right? The first one is the open system, and the second one is the closed system. So the open system is a system connected to a network, ready to send, receive, execute command across multiple hosts. So for access control systems like this, these are systems that needs network connectivity for them to function. So without network connectivity, they are not going to function. These are systems that you find in high-level environments. High-level environments where there is no fallback between there's no fallback when there is no network connectivity, right? So in this system, you can find it in banks. For banks, you can find a system like this in banks where there's always network readiness. If there's network downtime on any particular dot in a bank system, there's always a response, right? And we have the closed system. The closed system doesn't require any network connectivity. It operates entirely in a physical isolation, right? And it cannot be communicated with remotely, right? So for closed systems like that, they are what we refer to as standalone, right? Standalone access control implementations. For standalone access control implementations, you don't need any network connectivity. You don't need a software. All you need is the device. You register your users, and the system operates in a closed system. So which means no one can, come from anywhere. No one can from anywhere control the device, because the device is not connected to the internet. So it's isolated, it's kept and without any network control. So these kind of systems are also found in the banking industries, where you have the vaults, right? Vaults are generally closed systems also, and they are not connected to any network. All the authorities required would have already been set. Once they are set, they are removed from any form of network connectivity. So these two systems, they are also suitable systems, but they have different roles in which they play, right? So now, how do you as an installer, how do you troubleshoot systems like this? How do you work with systems like this? So to work with systems like this, you need to always troubleshoot from bottom up. So you can see in this funnel, I gave 3 layers, right? The physical layer, the transport layer, the application layer. So these 3 layers are essentials for you as an installer. As an installer, you must be able to troubleshoot from bottom up. And I included a phrase, which is a flawless IP configuration means nothing if there's a physical wire cut out. So one of the things you want to really pay attention to when you go out for installations is that you want to start your troubleshooting from the physical layer, which involves the cable, the device. Is the cable okay? So take for example, you are called for a support, right, at a client site. And the client is telling you that this device, we've been trying to gain access. It was working before, but it is not working anymore. We can't gain access anymore, right? When we put our card, when we badge our card on the device or our fingerprint on the device, the door lock is not opening. One of the things you want to do as an installer is to troubleshoot from the physical layer first. You want to troubleshoot from the physical layer. The first thing you want to do is you want to check, okay, is the cable connection appropriate? Is there a joining? What's the distance? You understand? What's the what connection was used? Those are the things you want to check first, right? In a closed system, those are the things you want to look at first. Is the connection okay? Is it what cable system are they using? Are they using an indoor cable where an outdoor cable is required? Is the crimping sufficient? Are they crimping the same points at every end? What's the distance? What's the power rating? Okay, this device uses 12 volt 3 amps. The customer is using 12 volt 1.5 amps. The device with power, but now you are now using it with you are linking it to maglock. The device will restart. So these are the things you want to really pay attention to first. Are they using the right power rating? What's the power rating of the device? What's the power rating of the lock? Right? What type of FCC button is used? Those are the things you want to first troubleshoot. Once you've checked that layer, you now tick it off that okay, the physical layer has been checked. So let's look at the transport and data link layers. Now, every layer has their own specific problem. So in this case now, the issue with the customer is that fingerprints is not a customer badge and the door is not opening. That's what the customer knows. The customer is not technical as you. They don't know what is happening. They just know that they put their card and the door is not opening. right? You've checked the physical layer. You've checked that the cable is right, the connections are right. So what is happening? Then you now check the transport layer. Okay, what is happening? The TCP/IP cable that was plugged to the device. The users that they are claiming that is badging the card or using the fingerprint on the device, is it getting the required access? Is this device, is it communicating with the software? That's in an open system. You want to check that layer. In a closed system, you don't need the transport layer. You just need the physical layer. But in an open system, you want to check the transport layer. Okay, is the cable working? Okay, when you ping the IP, did it ping successfully? These are the things you want to look at, right? And after you've done all those things, you've checked your commands, you ping the IP, the IP was able to ping successfully, and you still notice that everything is fine. The next thing you want to check is the software, which is the application layer. Is the software opening? Could it be software issue? You see, so as an installer, always learn to troubleshoot from bottom up. So it's called the bottom up principle. So always learn to troubleshoot from bottom up, from the physical layer, the data link layer, and the application layer in an open system. So now let's look at the anatomy of an access control ecosystem. For an access control system, for you to achieve an access control system, you need few things. First, you need the access control machine. In this case, it can be the device, it can be a biometric device, or it can be the controllers. You know, I've explained the controllers to us. We all know the type of controllers we have, right, at ZKTeco. And it's not just only ZK controller. It could be any controller, right? This is a general logic, a general behavior that exists between any form of system you are using, be it any form of system, even if it is not ZK, even if it is European locks, even if the lock is $200 million, it still boils down to just system. The system in this case is you need an access control machine. You need the mechanical interface. The mechanical interface is what? The electric lock. The electric lock can be the mag lock, cathode lock, strike lock. It could be anything. You need your door sensors. Door sensors are optional, right? In a closed system, you might not need a door sensor because a closed system means you are not monitoring. Then you have your exit switch, which is your exit button, right? Then you have your external reserve for slave connection. And you have your management center, that's your PC, right? So your PC is where you handle the software. Then you have the alarms, the other auxiliaries you want to add. So this is what makes up an access control system. This is the anatomy of an access control ecosystem. In some cases, this access control machine could be replaced with a device. It could be a controller. It could be anything. It could be a device with a GUI, one of our biometric devices, the one I showed in the last class. It could be one of our controllers. It could be one of a third party, but they still follow the same principle. And that principle, I'm going to be explaining that to us. So, but the anatomy of an access control system does not pass this diagram. And one of the things we are also going to be doing is I'm developing a gaming system for installers. So the gaming system is going to be part of the assessment. The gaming system is you go to the website and you arrange access control system. You build an access control system basically. So it's still in works. So it's probably going to come up in one of the assessments we'll be giving soon. So just to have that in mind. Now, so I was talking about the access control machine, right? The access control machine is the brain of the system. The access control machine is the brain of the system, and it can be in two types, like I told you. First is it can be in the form of our standalone devices, and it can be in the form of our controllers, right? So what I call them is first the edge device and the central panel. The edge devices contains all-in-one edge processing. So which means you have your biometric device. With your biometric device already has your GUI. It contains your reader for verification. All the logic, the relay logic, everything exists in this one device. The firmware logic, the database where the users are stored, everything exists in this standalone device. That's one case. The second case to it is the use of the controller. You see, the controller doesn't really have all the functions a standalone device would have. The controller has what we call a distributed processing methodology. So the controller itself combines this, each of the components of this, it combines them together. So let me give you an example. Say here we have a controller. So for a controller, you need a reader. The reader in this case is not a device, is a reader, just a reader. Something that receives information and sends information directly. It doesn't store information. Readers don't store information. Readers. And I showed us examples in the last class. For those that have been following the class, you know the examples of readers. We have the Wygan type of readers, the RS-45 type of readers, right? For Wygans, we have them in series, the KL series, that's for the ZKTeco type. KL series, Wygan series, and the FR series, you know, RS-45. So you have your readers. So what the readers is doing is to receive information and pass it to what? And pass it to the controller. Receives information and pass the information to the controller. Now, then we now have the mechanical lock. We have the mechanical lock, which could be mag lock or anything, right? Anything mechanical, right? Mechanical lock. So the mechanical lock is also connected to what? Is also connected to the controller. Then you have the PC also that is also connected to the controller, right? So this method, we call this method the distributed distributed processing method. So it's a method that uses this. because you are introducing a controller. So, but for the other method, which is the edge method, you already have the biometric device. The biometric device already has a GUI. It already has a small reader module, which could be a fingerprint module, right? It has a GUI that you can operate on. It has a fingerprint module. It has internal connection relay. It stores data. In some cases, it doesn't need software because it can work as a standalone. Users can be added to it. Users' data can store on it. You know, user registration can happen on it because it has a graphical user interface. GUI is called, for those that don't know, GUI is called graphical user interface. Because it has a graphical user interface. So you don't need to introduce readers because readers are already embedded on it, right? The only thing you are introducing is the mechanical lock that this will control. So, but this edge processing device has abstracted this guy. What this guy is doing, it has abstracted it to one. But there is still an advantage a distributed system have over a single system like this. For a distributed systems, using a controller can come with multiple relays. A controller can come with 2 or more relays, but an edge system, which is the use of a device, only comes with 1 relay. So for this controller, I can add up to 4 mechanical locks to a controller. But for devices, I can only achieve 1 mechanical lock units. You understand? Because this guy is an edge device is an edge processing device with only 1. But a controller can take 1 or more mechanical locks, can take 1 or more readers. Right? So that's the difference. So it's why it is termed a distributed processing device. So for the architecture, for standalone devices, the edge brain, all-in-one edge processing contains the reader, verification database, firmware logic, physical relay, entire. Then for the centralized brain, which is the distributed processing architecture, the reader sits at the door, but all verification, firmware logic, relay switching occurs safely inside a locked IT closet, which means this guy here is stored somewhere that people don't know about. The readers are just interfacing. So for products like this, the system itself is isolated away from users' purview. But for systems like this, the users are seeing it. They know that all the database exists on it. That's for the edge brain devices. So it is easier for vandalism to happen on this device, because if this device is taken away, it means all user data is gone. That's for standalone units. But for this, even if the reader is taken away, you still have your controller and your user data intact. So those are the pros and cons to using systems like this. So, and each of these architecture depends on the it depends on where you are installing at. It depends on the customer preference. It depends on the nature of the job you've gotten as an installer. Say for example, a company wants to install access control units at their storage area, just one door at their storage units, right, in their facility. You already know for systems like that, a standalone edge access control is sufficient because one, where you are installing is in their facility. Their facility is already guarded. So systems like this becomes easier to deploy. But in a case where you now have the customer reaching out to you that they want to install, they have 10 doors, 20 doors access control, and they want to install, then you have to now look at how you want to distribute each of those processes by introducing what? A controller. A controller will help you distribute those processes. One controller, you can achieve 4 doors, and with one controller, you achieve 4 doors. 5 controllers, you already achieve 20 doors. So you want to look at systems like that too. Now, so for these 2 processes, what happens? What decision takes place when something like this happens? What is the internal logic decisions to unlock? So the first thing is the user swipe. The system, when the user swipes on the device, the system verifies, is this ID that is swiped, is it valid? If it is valid, continue to the next step. If it is not valid, output error, right? If you do it consistently, trigger alarm and keep it locked. That's unauthorized access. Unauthorized access. We've seen those movies, right? Where an unauthorized person walks to a system that has an access control and they try to verify, then you get this trigger, right? So is ID valid? If it is valid, then the next thing is this ID, is this part of this particular access groups? So in a system, so let's say you have an organization that has an architecture of, say, 10 doors. Out of that 10 doors, the MD can only access out of the 10 doors, the MD can only access 3 doors. The accountants can access 2 doors. The security personnel can access just 1 door. These are access groups that you are creating. So in those access groups, you are classifying those 3 doors that the MD can access. You are classifying them under a group, MD's access. You are creating another access group. You are classifying them. Don't worry, you are all going to see how this happens on the software. So, but you just have to keep notes. So you are classifying another group. Okay, security access. Now, when a user goes to a particular door, the system will check. First, is this user valid at all? Okay, yes. If this user is valid, if this user is valid, the next step is add the valid access group. Access group. If you are authorized to access that particular door, the next thing is the system wants to check if you have a valid time zone to access that door. So the system acknowledges that, okay, although you are authorized to access this door, but are you authorized to access this door at this particular period? If you are authorized to access, the system allows you and it moves you to the next step. If you are not authorized, you get time zone deny error, like, okay, you are not authorized to access this door at this particular time. So all these things, they happen instantaneously, but this is the flow in which they happen. Then the next step is the anti-passback. Have you accessed this door before and have you exited? So this is an optional settings that also happen. More of this is going to be explained in our next classes also. So then when all these accesses have been given, then you now have your then the system can now trigger the relay to what? To unlock. So this is what happens. This is the internal logic decisions that happens during access control implementation. So now we've been talking about the access control. Let's now look at what happens internally, right? What happens internally to this relay, right? How does this relay trigger? How does when using a mouth clock, what happens? How do what type of actions is expected of the relay before it triggers, right? We now have to pay attention to these concepts. We have three concepts three terminologies we need to pay attention to. The first one is the common. The second one is the normally closed. And the third one is the normally open. These are the three terminologies used by a relay system, right? So let's now explain how it works. In a simple access control, every device, any form of device, even if it is not a ZK device, even if it is another device, I'm sure some of us are experienced, but for those of us that don't really know about stuff like this, one of the things we want to pay attention to are these three terminologies on every device. Every device would always have this. Every device that supports access control would always have this function. And the more of this you see on a controller, it tells you the more relay that is present on that controller. So they have this function. We have the NC. We have the NO. We have the common. So these three functions, they are very important. So, and here's how they work. Say you have a relay, right? And say you have a 12 volts, 12-volt adapter. So the reason why it's 12 volts is because low voltage products works generally using 12 volts. So you have the positive, you have the positive point of the adapter. And you have the what? the ground. Here we call it GND, right? For those that don't know, this minus sign in some cases is called GND, right? On your lock also, any of your mechanical equipment, we also have 2 points. Your mechanical equipment, we also have the positive. Listen, and the ground, the negative, right? We all know, we all understand this. Now, if in a relay system, right, everything is basically electrical flow. No, for you to have a flow system in electricity, you need the positive to start the journey. Then you need the negative to end the journey, right? So you need a positive to start the journey. You need a negative to end the journey. So you achieve a what? A closed circuit, like a closed flow. Now, in this system, in access control system, you have the AC connected to the positive of lock. Lock, mechanical lock. This could be a lock, this could be anything, like anything mechanical, you know. You have the NC, that's the normally closed. Then you have the COM to the 12-volt adapter. Then you have the ground. In this case, what have you done? You've created a flow, an electric flow. Current is flowing through because you've completed a flow. NC means normally closed. It means you are completing the circuit. So it means current keeps flowing from the 12 volts to the lock, to the device, from this 12 volts to the lock. The device is allowing that flow. It's just like saying, if I remove this guy, and I bring it here, current is flowing from my lock. If I plug my 12 volt to my lock directly and my ground to my lock will turn on, right? So, but in this case, we want to achieve an access control, a simple access control implementation, right? So let's say this mechanical lock is a magnetic lock. We all know that magnetic lock uses what we call electromagnetic induction, right? Electromagnetic induction basically means in this one, you have your electric lock, then you have your magnetic bar. In this electric lock, you have a coil in it. How many of us know Faraday's laws of electromagnetic induction? Good. So, magnets, right? When a current is induced, it attracts, right? So now, for you to start this induction, for this lock, this magnet, you need positive and negative. You need it to be connected. So when you connect your 12 volts to this lock, and your ground to the ground of the lock, this electric charge gets induced. So magnetic bar can get attracted to it because this has been connected to power, which is this 12 volts, right? For magnetic bar, you can use any volts. You can use 5 volts. You can use, for a magnetic bar, can take from 5 volts upwards to 12 volts, right? The more the voltage, the more the strength of the more the induction, right? So the magnetic bar would attract because this is currently powered. Is currently powered. When power is cut out, right? When power is cut out, what happens? This stop attracting, then the bar gets what? Released. It's as simple as that, right? Are you with me? If you are with me, please drop a thumbs up. Yeah. Let me leave room for questions before continuing.
Hello, sorry, sir. Can you recap the last part? The last part.
Yeah.
Can you recap, please?
Can I?
Can you recap the last part? That's
Okay.
power that removed. Can you recap, please?
Okay, I'll recap. Yeah. Wait. Who else? Who else wants to ask questions? Yeah. Edwin, can you mute?
Yes.
Edwin, can you mute? Yeah, I can hear you.
Okay, I should mute. Okay.
No, yeah, you are cracking. So you can drop your questions. For you, you can drop your question in the chat. Will, you want to ask a question? Will.
Sorry, please. I was not asking a question. You said
Oh.
with thumbs up, people can hear you. That was a mistake. Sorry,
okay.
I'm with you.
Ismail. Yeah. Okay, good, very good. Ismail. Okay, I think Ismail too is the same thing. Okay, so let me go back. You know,
can you hear me, sir?
Yes, I can hear you.
Yes, what I'm trying to achieve is I follow this step up to when you explain common, the normally close, the normally open, and when you are like depicting the flow of the voltage, the positive of a adapter to come, and you said from normally close to positive of the lock. So other connections around it is not yet well explained. Maybe you can just help us.
Okay, so just follow me, follow through. You
Yes.
see, when I'm taking something like this, I like to like really go like I like to really go deep, right? Really explain it from the principle, because by explaining it from the principle, it will let us understand how they work. So have we all seen a mag lock before? If we've seen a mag lock before, please thumbs up. A magnetic lock. For those that haven't seen a mag lock before, a magnetic lock. So for those that haven't seen a mag lock before, let me just magnetic lock. Can you see my screen? For those that haven't seen a mag lock before, this is how a mag lock looks. You have the magnetic lock itself, then you have the bar, right? This is a mechanical lock used for access control. It's one of the common mechanical locks used for access control. So you can see one example here. You can see that you have it. I'm sure if you've seen this, a lot of us that goes to different offices will see this in various offices. So if you haven't seen a mag lock before, this is how it looks like. Right. A magnetic lock is used to restrict access. That's the work. And how do you achieve access restrictions with a magnetic lock? in a maglock, let me copy this image. I think I can. Good. Okay. You can see my screen, right? You can see my screen. Good. So this is a maglock, right? What this thing beside it is the magnetic bar. This itself is the magnetic lock. In this magnetic lock, there is a coil induced in it. There's a principle we call the electromagnetic induction. Right? So electromagnetic induction happens when, so let me show you an example. So it states that when a coil is induced with current, it generates a force of attraction. So, and when you direct the north pole of a magnet to that force, it attracts that. That's the principle of electromagnetic induction. This principle is used in different cases. We all know loop detector. It is used in loop detector, loop coils. The principle is simple. When you loop a coil, like when you coil something like a wire together, a copper wire, when you coil it like this, right, and you take the first end of that coil, you put it on a positive current, you take the second end, you put it on a negative, it generates a magnetic force. It generates a force field. That force field that is generated attracts magnets. It attracts the north pole of a magnet and it repels the south pole of that magnet. Do you understand? Now, that principle is what is used in an electric lock. When you pass an electric current into an electric lock, when you pass electricity into electric lock, what gets induced is that coil. The coil in this lock generates a force field. That force field is what attracts this bar, this magnetic bar you are seeing here. Do you understand? So when you place the bar on this, so the bar is basically placed on this thing, this white stripe that you see here. So when this thing is powered, when you place the bar on it, it attracts it. You won't be able to remove the bar. So normally, if you check this door, you'll see that the bar is on the door and the lock is on the frame. When this gets induced, once you close the door, this mag lock gets attached to this magnetic bar gets attached to this mag lock, because this mag lock is already induced with currents and it has generated a force field. So when you remove this 12 volts, when you cut power, me removing this thing, it means when you cut power. You understand? When you cut power, now I'm taking power away. The force goes away. You understand? When the force goes away, what happens? The magnetic bar would disengage. Yes or no? True or false? Exactly.
True.
how does this relate?
Yes. It's true. You are making sense.
So now, how does this relate to access control? In access control, what our relay is doing is ensuring that the current is either distributed or not distributed. Our relay is a middleman. Now, I want to add a middleman. You know, instead of having this positive and negative to the lock, I now want to introduce a middleman. The middleman is the what? The device. You understand? So, a relay has 3 points. The normally closed. Normally closed means that the circuit acts like it is connected to a 12 volts. It acts like this. It acts as though the lock is connected to a 12 volts. It's not breaking the voltage. So current keeps flowing. So the lock is energized. If I move it to normally open, here like this, it means this will not be energized. This is going, the NO is blocking the circuits. That's why it is called normally open. It means the circuit is open. When a circuit is open in electrical terms, it means there is no current flowing. When the circuit is closed, it means there is current flowing. You understand? Now, for locks, because of the nature of the lock, right? The nature of access control is that you always want to keep the door what? You always want to keep the door closed. And to ensure that the door is closed, right? What happens? You introduce this system, right? Your NC connects to the positive of the lock to ensure that the circuit is intact, so the lock is closed. Now, remember I said this is a device. This will be a device, or a device would have this. A controller will also have this device, or you understand? A device would have this. A controller would also have this. A device would have NO, NC, and COM. A controller will also have NO, NC, and COM because they are serving as the middleman, like I said. So now, when a user, I need to draw a little stick man here. When a user comes to punch their card on the device, what happens is that immediately they punch their card, NC disengages and current stops flowing to the lock for a particular period of time. Do you understand? This image I'm showing you is the image of what happens in a relay. In the relay, this small pin it disengages. Once it disengages, the lock opens. The magnetic bar releases. You understand? So once it releases for that period of time, because the relay is attached to the logical control of the device, so the device can decide how long this pin should disengage. That's why on device you see that 5 seconds, door should open for 5 seconds, 10 seconds, 15 seconds. It means this relay pin will disengage for 5 seconds. So it means for 5 seconds, the door is open. The user, after access, the user can enter inside and come out, after 5 seconds. Once it's 5 seconds, the relay works. It gets attached back. The pin falls back into position. Then the lock works. The lock shuts. Then the magnetic induction coil, it happens, it coils again, then the magnetic bar energizes again. Like, do you understand? Do you understand? If you understand, thumbs up. If you don't understand, raise your hand. Yeah, good. So this is what happens in a relay. This happens in every system, every security system, no matter the brand, relays. This is the principle of a relay, no matter the brand. You understand? So let's go back to our slide. So when the device verifies a user, NC is normally closed. It means the circuit is closed. When there's verification, this pin releases, the circuit becomes open. For normally open means the circuit is open by default. When verification happens, the circuit closes. So when the device verifies a user, it sends a firmware signal that mechanically flips the relay state. Can you see? NC becomes open, NO becomes closed. When verification happens, this is what happens in a relay, as simple as that. So when it comes to lock, for standalone implementation, this is the simple way to connect a device to a lock. Simple mechanism, simple methodology. Your normal close to your lock positive, your COM to your adapter, your ground, use your ground to complete the circuit. I want us to pay attention to this, very important. So now, there are different types of lock. In a magnetic and electric mortise lock, they require power to lock, just like I explained for magnetic lock, and same thing with electric mortise lock. Power must be cut off before they open. You understand? If the power fails, these doors unlock automatically. Then you have the second part, which is the fail secure, the electric strike lock. Electric strike lock, you must supply power for it to open. By default, electric strike locks, their state is what? Their state is locked without power. If you get an electric strike lock, you see that it's always locked. But when you put power into it, that mouth becomes free to open and close. I don't know if we all know electric strike lock. Let me show us electric strike lock. I'm sure majority of us would have used something like this. Let me look for a picture I can get here. This is one. Yeah. This is how electric strike lock looks like. Can we see? This is our electric. So when you get this strike lock, you see that this part is always very hard because this part is what latches to the door. But when you connect it to power, it becomes free. You understand? Yeah, someone wants to ask a question. Okay. You understand? So it is why electric strike lock requires power to unlock it. But for the fail-safe principles, they requires power to be cut before they are unlocked. But for fail secure, they requires power to open. You understand? So that's the difference between fail safe and fail secure. So connect for mechanisms like this, you need the NO, because by default, this requires electrical circuit completion for it to open. The default state is that power must not be supplied to it. It is when verification of access is needed, that is when power should be supplied to it. That's when that pulse of current should be sent to it. But for magnetic lock and multi-locks are the ones we use for our smart locks. Those smart locks that you purchase. You understand? So those are the two differences. I want us to pay attention. Now, for the standalone architecture of a device, I've explained to us, but this is the architecture. You power your device, your mag lock, your NC to your lock positive, your ground to ground, your COM goes to your power supply. You know, so this is the principle. Then you supply your 12 volts. So this is the principle of a standalone communication. Then you have your exit button, right? Your exit button will always come with a positive side and a negative side. So you connect that. So I hope that's clear. Now, let's now come to readers. For readers, there are two types. We have the Wigand. There are two types of protocol that readers uses. I'm sure we all know examples of readers. There are two types of communication mechanisms that readers uses. You know, we've explained mechanical lock to controllers, mechanical lock to device, right? Now we want to explain readers to controllers. You understand? Devices already have readers embedded on them, right? So we want to explain readers to controllers. And the protocols, let me share this tab. I wasn't sharing this tab. So, you know, we've explained mechanical lock to controller, mechanical lock to device. Now we want to explain readers to controllers. For edge devices, they already have their points. But in this case, you might also want to sleeve a reader to them. Say you want to do reader in, device in, and reader out. So now we have readers. Readers are just products they are products that don't store information. What they do is they receive information and send it immediately to the respective device or the respective controller. And we have those communication in two types. We have the Wigand and we have the RS485. Two protocol. We have the Wigand, we have the RS485. The legacy way is the Wigand, which is the old way. And I'll explain that, why it's the old way. The modern one is the RS485. And RS485 is not even as modern as the OSDP. OSDP is called Open Supervised Device Device Protocol. Is another form of RS485. Now, for Wigand communication is simple. you have the data 0, data 1, GND, and what? Your 12 volts. These are the three communications. When you see a reader, you want to search for this. And when you see a device, you also want to look at the device, the back of the device, and note this. You will see WD. If you don't see WD or WD1, you see D0, D1. This is a standard on devices, not just ZKTeco device. The training we are giving you here is to understand the basics. When you understand the basics, you can work with any devices, even if it is not ZK. You understand? So you have the Weigand data 0, data 1, GND, and 12 volts. The function of a Weigand, why it is legacy, is because Weigand only has the capability to transmit code, to transmit numerical code into bits. Its transmission is simple. It can only send ID to the controller. It can only send numerics like 1, 0. It can only convert numbers into bits. You understand? But RS485 has much more capability. RS485 can store images, converts those images into bits, right? It can store images, convert those images into numbers, then those numbers can be translated into bits. So RS485 communication protocol is what allows the birth of biometric communications, which is your fingerprint, your card, your fingerprint, your face print. You understand? Everything is achievable through the use of what's your RS485, because RS485 has the capability to convert fingerprint images or facial images that are stored in base 64 into bits of numbers, into numbers that can be converted into bits that can in turn be translated in a controller. Modern weights, you understand? Yeah, Sholoton. Sholoton, you want to ask a question? Yeah, you can ask your question.
Okay. I just want to confirm something. It's not as if I want to ask question. This RS485, it answered the questions that I asked last class, that I want a device whereby they can snap and they will take the picture of that person and submit it to the system, and whereby the person is coming again, they can easily snap the picture of that person again and search the database and get the person. I think this RS485 can do that. I just want to confirm that.
So biometric devices are what we achieved at. You understand? Biometric devices, they have the capability to take facial images, and they have the capability to read facial images. You understand? Biometric devices themselves can achieve that. But when we are now talking of readers, readers now use a protocol which is called the RS485. The RS485 is not a device. Don't get it wrong. The RS485 is a protocol that allows a reader to communicate with a controller. So let's say we have a controller. If we have a reader that reads face, You understand? A reader that reads face. That will work in your case. It means we can get that controller and get that reader that reads face. But in your own case, why go through this route when you already have a biometric device that reads face? Just like those devices I shared with you in the last class. Those are biometric devices that reads face. They can take facial prints, store facial prints. Then when you have someone come in, you want to verify that facial prints, it can be verified. Simple as that. So that is in that case. So, but this in its entirety is a protocol. Is a protocol that allows peripheral readers to transmit information to controllers. Peripheral readers cannot store information themselves. What they do is to take information and transmit it to the controller to interpret. And those readers, they don't have memories. They are just what you slave to a controller. One example, although I shared this with us, is, let me give you an example of a ZKTeco reader. I'll give two examples, which I'm sure most of us have seen before. So one example of a reader is this. This is one example of a wide-band reader. This is a card reader. Can you see? Can I see my screen, right? You understand? These are readers. These are readers. You understand? These are examples of a wide-band readers. They don't store information. They just take and transmit that information to the controllers. So this is an example of a wide-band reader. This is an example of an RS485 reader. So you can see the difference. You can see that this reader has a fingerprint terminal. It also has a card terminal. See, you can see it, right? Thumbs up if you can see it. So this is an RS485 reader. You can see that these readers, they are different from devices. These are different from devices. They are readers. You understand? This is a wide-band reader. You can see that it has no fingerprints parts, only card interface, keypad interface, because it can't store fingerprints image. You understand? You can see that these are different from devices. Devices are biometric devices that I shared with you in the last class. An example is something like this. I shared this type of device to us. If anyone, people, what's the model of this device for those that joined the last class? Anyone? What's the model?
No, it's Palm
Yeah?
10.
SF100,
That's,
SF200, SF300.
SF, no,
This one.
FR400.
No. This is speed face. This is speed face, the visible light devices. This is the speed face device. This device, you can see the interface, it can read face, it can read palm. Please, I want us to go back to the slide and look at the device. It's important to know the models. I know it's not going to be easy now, but always make sure you get yourself acquainted to ZKTeco models, so it will be easier for you to know. So let's proceed. So these are the two protocols that we have: the RS485 and the wide-band. So for the alarms, alarms are also sensors. They are peripherals that, you know, integrates to device. They do not require power themselves. They require external power, So on the relays, you can see on the devices, you see them as AL minus, AL plus, or NO2 COM2. So you see them as this, So for sensors, they are used to detect the state of doors. On the device, you see them as sensor and GND. This terminology is the same for every equipment. It's the same. If it is not like this, they will write it in full for you. So it's a standard. So for advanced options, which we are going to be treating in the next class when we are talking about the software, we're talking about the time schedules, the access group, the anti-passback, the duress options, right? We want to look at those parts. Now, this is now the complete digital flow I've been talking about. For you to have a good mastery of access control, you want to understand the entire loop from abstraction down to implementation, right? You need to understand everything down to the execution, which I've just explained. In our next class, we'll be looking at software's connection with these devices tomorrow. But I'm sure we all understand the simple connection terminologies now. So you can see your lock to the door. You have your controller. Your controller has this NO, NC COM. Then you have your readers that supports the trigger. For fingerprints, it uses the RS-485 bus line. Then you have your TCP/IP command to the controller. You need to have this idea on how these systems function. Now, so lastly, this is a holistic overview of ZKTeco controller, the ZKTeco biometrics controllers. This is all the components that exist in these controllers. All the logical units, from the Wigand to the RS-485 to the sensors to the log. You can see so many NCs and COMs. This is the topology that exists. For these controllers, I explained in the last class, you have them in 2 doors, 2 doors, 1 door, 4 doors. You understand? So I want us to really pay attention and go through this and look at it. This slide will be shared with us. Tomorrow, we are going to be looking at how the software connects to the controllers or the devices, the connection mechanism, TCP/IP layer. We'll be looking at that. We'll start with bow time. We'll look at how the connection is made in general tomorrow. By next week, we'll split it, bow time and CV security. We'll now dive into the softwares and how the software works. So do we have any questions? Any questions from today's class? Any questions from anybody? Yes, some people, so yes, the slide is going to be available to us. Someone said, can controllers be slaves to one another? Yes, generally controllers can be slaved to one another. But when it comes to ZKTeco controller, you can't slave ZKTeco controllers to one another, because slaving controllers to one another is a legacy form of implementation. Controllers like that are passing controllers, the old passing controllers, some linear controllers that you slave to one another. But for ZKTeco controllers, you are adding each component on the software. Once they are added on the software, you can logically group them, you can logically combine them, you can logically separate them as you want. So we are going to see all those in this training. So let's take quick questions. Do we have any questions? This slide will be shared to us. We'll continue tomorrow with the software connections to the devices, how they connect, the underlying principle of how software connects, the different types of software, web-based software, application-based software. We'll be looking at that. We'll be looking at how they work and how everything is structured. So I'm bringing this to the end of the class. In the absence of questions, let's keep our conversation in the group. Let's help one another in the group. Someone said, how effective is this maglog? Yeah, maglogs comes in different types, different weights. You know, and maglog is not ZK, is generic. You can get them from anywhere. Different weights, and they can take from 5 volts to 12 volts. So the last week's slide have been shared. If you check the group, you see the link to the repository for week 1. Open week 1, you see the resources for week 1 in the week 1 group. We are currently in week 2. Resources for week 2 will be shared after the after tomorrow's training. You understand? So thank you very much, everybody, for joining the class. I hope you all gained something. Someone said, can devices be slaved? Yes, devices can be slaved to one and other, but if you are slaving devices, you have to ensure that they are the same devices, or they are devices that has like the same architecture. So for example, if you have MA300, so you can slave a reader to MA300, but you need to know, because MA300 doesn't have a GUI, it doesn't have a graphical interface, so you need to check the documentation of MA300 to know what to be slaved, what type of reader you need to be slaved to MA300. So, but generally, you can slave Wygan readers. You can't slave RS485 readers. You can only slave Wygan readers. So, right. Thank you very much for these sections. Tomorrow we'll continue. Let's keep the conversations in the group. Let's engage each other. Let's engage each other and have a good day ahead. I'll see you guys tomorrow, same time. Thank you very much.
Thank you, sir. Thank you so much.
Thank you, sir. We really appreciate it.
Thank you. Really appreciate it.